Hello students, welcome to Smart Engineering Tutorials. Today we are going to see another topic of Unit 1 of Communication System subject, and the topic is probability density function. So before seeing PDF, we have to know something about continuous random variables. Like discrete random variables, they have a fixed value, particular certain value at a certain value of x. But if you talk about continuous random variables, they don't have a particular value, but they have a value which is in some range, and so we say that it has some continuous values. For continuous random variable, let's say x, it can assume any value in a certain interval. So the probability p of x, this is the random variable, that it has this random variable x has a value of xi. So this probability tells this. The probability is actually 0, because in continuous random variable, the probability that it has a particular value, it's really 0, because it will not have a particular, but it will have a range. You cannot predict that it will have this certain amount of value. For example, we'll see, if you talk about temperature, the temperature, you cannot predict that it will have this particular value at the instant of time, but it can have a range of values. So in that range, it can take any since in that range there can be infinite values of the temperature. So actually infinite values exist. So we cannot know that the random variable, if you talk about the temperature T here, that the random variable T has a value of Ti. Predicting this is impossible, and so we say its probability is 0. This is the difference between discrete random variable and a continuous random variable. So for continuous random variable, the probability that x random variable will have xi value is not meaningful quantity, because you cannot predict this. And if it is 0, then how come we are going to analyze it? So we are not going to use a certain term, but the probability term which we are going to use here is that the random variable x will have a value from x to x plus delta x. So it will have a value in this range. This will create some meaning because it is a continuous value. So for seeing the continuous value, we will use CDF term, which is more useful for continuous random variable here. It will be very useful here. So we'll start from there. Since the probability that the random variable x has a value in the interval x to x plus delta x is actually, we already saw CDF. So how can we calculate this? Is the difference between the two intervals. It is a difference of CDF at these two intervals. That is, and we know that CDF is actually the probability that this random variable is having a value equal to or less than that particular instant or that particular value of x. Already seen, you can see, go through the video of CDF again. So this probability is written as fx of x plus delta x. That is the probability that the random variable will have a value less than or equal to this, minus CDF of x, that is fx of x, random variable x having a value less than or equal to x. So we have written this equation. And if we talk about, now moving into deriving about the PDF term, now from the equation of CDF, we have seen that in a previous video that fx of x2, where x2 is greater than x1, we have already calculated. This is equals to probability that random variable x will have a value less than or equal to x1 plus probability that this random variable x will lie between x1 and x2. So this actually is a CDF, fx of x1, and this is the probability that x random variable will lie between x1 and x2. Now using this principle, that we will apply it to the range which we have already talked, that this random variable x will have a value between this in the interval x to x plus delta x. We will use this and calculate this by using the CDF principle. So fx of x plus delta x, following this principle, we can write here that it is equals to fx of this random variable fx of x plus probability that this random variable lies in the interval x to x plus delta x. I have written it as equation number A. Now using a Taylor expansion for delta x approaching 0, we can write the same equation as fx of x plus d by dx of fx of x into delta x. And after using this limit tending to a 0, we have used this Taylor expansion. And from a and b, if I compare, these both are equal terms. That is, limit delta x tending to a 0, d by dx of fx of x into delta x is equals to actually this probability that this random variable will have values in the range x to x plus delta x. So we have got these ABC equations, and here the term this d by dx of fx of x, that is the derivative of the CDF, is actually called the PDF, px of x, which is PDF of the random variable x. And this is the new equation d, and this is the PDF term which we are going to see in detail. So actually the PDF can be obtained by taking the derivative of the CDF. So equation number C, which we have already seen here, it says that the probability of observing the random variable x in the interval from x to x plus delta x is, we have already seen in the interval x to x plus delta x is, this is actually the PDF and this is delta x. So we can write it as px of x PDF into delta x when delta x is approaching to a 0. So this is the product of two quantities, and actually it is, if I say that this PDF is a curve, so this is actually telling, and since the range is from x to x plus delta x, so the difference in the interval is delta x, and we are multiplying this PDF with that interval. So actually it is the area under PDF, px of x, over the interval delta x. You can see this through a graph. I've already drawn it here. This is the PDF and this is the graph of your PDF, and here this distance I've shown here, this is delta x. So actually this px of x into this delta x is giving you the area under this curve over the interval delta x. This is what I've shown here. So moving ahead, the equation number D, which we have obtained, from there we can see that the CDF can be obtained from PDF, but how? By taking its integration. And we are integrating it from, since it is having a value of x, this fx of x, actually we are taking that the probability that the random variable x will have a value x. So that's why we are integrating it from minus infinite to the value x here. And we know that fx of minus infinity is 0. That is, the CDF of a random variable, that the random variable will have a value less than or equal to minus infinite, is an impossible event. It will be 0. The probability of this thing is 0. So we can write this as minus infinite to x. Now the probability that random variable x will have a value from x1 to x2. So we can write it easily. We have already seen in the last video, we can write it as fx of x2 minus fx of x1. And now this CDF can be written in terms of PDF, minus integration from minus infinite to x. And here, since the value random variable is taking value x2, so we will write as minus infinite to x2 px of x into dx. And here it is, the random variable x is taking value x, so we will write minus integration minus infinity to x1 px of x dx. So this is actually, we can write it, since minus, we have already seen that fx of minus infinite is 0. We know this thing, and if I see this mathematically, we can write it as x1 to x2 integration from x1 to x2 of the PDF px of x dx. So we term it as equation number E. So to find the probability between the two intervals of the random variable x, we can take the integration of its PDF. So moving further, thus the probability of observing x in any interval x1 to x2 is actually the area under the PDF px2 over the interval x1 and x2. So we can see this again in the graph, that to find the probability that the random variable x is having a value between x1 and x2, it is equal to the area of the PDF graph over this interval. So that is what we have seen through this equation number E. And moving further, we know that the fx of infinite, that the random variable x will have a value, probability that random variable x will have a value less than or equal to infinite is 1. So this is a certain condition or certain event. So we know this using this condition or this fact. Here we had written from minus infinite to x, and we use this fact, and now using this fact we have obtained this equation. And now along with this equation and using this fact that fx of infinite is 1, and merging these two facts, what we get? Minus infinite to infinite integration of px of x dx will give us 1, because this fx of infinite is 1. So we get this new equation number f. So as we can see here, this integration of PDF is equals to 1, and this equation is a property of PDF that every PDF must satisfy this equation number f. That is, whenever we integrate any PDF from minus infinite to infinite, it will be 1. And actually this is the probability of observing x in the range minus infinite to infinite. And since it is a probability, therefore this PDF is a greater than or equal to 0, that is, it is a non-negative quantity. So that was all for today's video. Thank you, and subscribe my channel for further notification. Thank you.